So in this chapter, we're finally looking at experimental design and hypothesis testing. We've already learned a lot about how to describe and present data. Now it's really time to perform statistics on our data and be able to either prove or disprove the hypothesis that we set out at the beginning of our research. Okay, so the goals for this chapter are to go through experimental design and how we can implement controls to try and isolate the variables that we're trying to study for our experiment. We then want to be able to apply what we call hypothesis testing with an understanding of p-values, test statistics, and levels of significance and confidence. So in terms of statistical tests, in later chapters, we're just going to go through a whole bunch of different types of tests that we can perform on different types of data sets. You can perform different statistical tests to see if two values correlate with each other, to see if multiple variables correlate with each other, and so on and so forth. But these are things that we can tackle later on. First, we have to understand how to set up a hypothesis and how to prove or disprove it. So let's first start off with an overview of statistical inference. So let's take a look at what statistics are and what parameters are. Then take a look at hypothesis testing and parameter estimation, because they have very different approaches. So statistical inference is the process through which inferences or predictions about a population are made based on statistics that are calculated from your sample data. The statistics are from the sample and the parameters are from the population. So this means that there are two approaches to statistical inference. There's hypothesis testing, which means we make a decision about a value of a parameter based on a preconceived idea about its value. So basically with hypothesis testing, we're saying the hypothesis is that x is equal to 20. But then when you take the measurements, you could get another x value, and you can see and correlate you can try and test to see if your measurement is similar to what you had set out to be your original hypothesis. And afterwards, we'll be discussing what the null hypothesis is. With parameter estimation, we're estimating or predicting the value of a parameter. So it's no longer us saying we think the value is x equals 20. It's now let's try and figure out a meaningful value for this parameter, which can be used in the population. So with hypothesis testing, we must first come up with a hypothesis, a value for the hypothesis and its contradictory hypothesis, the null event, and then either reject or accept it and make conclusions. With parameter estimation, we have to look at the estimators as well as the maximum likelihood of getting certain values. So we're going to start off with hypothesis testing in this chapter. Then we're going to take a look at parameter estimation, and then we'll take a look at a bunch of different tests that we can use. So steps for experimental design. Let's take a look at what the recommended steps are, and then the types of controls that we can use. So experimental design is a very complex process. It's simple, but there are a lot of steps involved. Overall, experimental design is the process in which you're trying to investigate a hypothesis. It involves deciding what factor is your independent variable, that's the one you want to be in control of, the one that you want to manipulate, and which one is the dependent variable. For the independent variable, though, we call that a factor, as in if we manipulate this, is it going to affect our dependent variable? And so we call the independent variable a factor, and adjusting it allows us to control the different factor levels it's at. So we then adjust the factor to see its effects on the dependent variable to determine whether there is a causal relationship between the two. Afterwards, once we have all of our results, we can apply a statistical test to either reject or accept the null hypothesis. So let's first go through the steps for proper experimental design. The first step, as I explained in the previous chapter, we should probably understand what we're looking for. So that means we should be able to understand and consider all the variables that will affect the experiment and consider whether they're related or not. Then we're going to see if we can present a testable hypothesis specific to what we're looking for. So as in, we predict that this is going to happen. Then we're going to design an experiment or a sampling routine to collect data and manipulate the independent variable so that we can see if there is an effect between the two of them. Then we're going to apply the appropriate statistical tests to see if what the p-values are. So that's something I'll talk about later. But once you get p-values and a level of confidence, we can analyze the results for significance, check for optimizations to see if we can improve the data that we've measured, and then we can repeat number 3 to 5 if required and get new forms of optimized data sets from a better experimental protocol. So after you're done with all that and you're happy with your results, you can summarize, present, and discuss your findings and conclusions. So first of all, we need to be able to understand what a control does. And so controls are something that must be introduced into any experiment, and it helps to remove the effect of other factors outside of the one that you're studying. So there are various types of controls that you can apply to an experiment, but the shared goal amongst each of them is that by the time you apply the control and collect data, you should be able to easily remove the effects of the environment, let's say, using the control, which we call the negative control, and be able to just notice differences from our manipulation of the independent variable on the dependent variable. So 4 different controls to be aware of. Experimental control is when you control the environment around the experiment. So this is very, very tough. You can control the temperature, you can control the humidity, and so on and so forth. But as you can see, if you control too many things, then it becomes very ideal and not so realistic. Number 2, it becomes very expensive. So if you want a clean room with temperature control and humidity control and many other types of control, that can get very costly. So in some cases, experimental control and environmental control is very difficult to achieve. So we usually use statistical control. So in that case, instead of adjusting the environment, we can record the environment settings and make sure that we do the experiment in similar settings or analyze the effect of those settings afterwards, just so that we see whether it can be factored out from our final data set. So these two, the first and the last one, they kind of go well together. Now, with a procedural control, that's when you run an experiment on a negative control group and an experimental group. So you've probably heard of the placebo effect before, and when people can actually get an effect from one drug in terms of the treatment group, where they actually get the real drug, and then the other group, the negative control group, they get basically a water pill, something that does nothing. And if they do exhibit an effect, it's called the placebo effect. And those effects can be removed from the treatment group so that you can see exactly what the drug will do to the patient. So in many cases, you do want to run a negative control group and an experimental group to make sure any factors arising from the procedure itself can be eliminated. So in that case, if you're running an experiment and trying to test whether, let's say, factor A is going to affect the signal intensity of whatever you're measuring, then maybe it's good to have a control where you don't add anything to see, to have a baseline measurement. And then it's good to have an experimental group where you actually do make those modifications to your independent variable and see what the measurement is like and what the distribution of data points are between the two, so that you can remove the effect of the environment and anything else from it. So that's procedural control. Then there's also temporal control. Temporal control is usually very important when you're observing two groups prior to manipulating factors. So if you have an experiment planned and it's going to go on for a very long time, you don't really know how time is going to affect your data set or your experiment. So sometimes it's good to let the experiment run for the first, let's say, few minutes or a few hours or even a few days, depends on what you're looking at. So let it run for some time, make observations to see if time affects it at all due to certain factors. And then you can start taking measurements and making your modifications to your independent variable. Then you'll be able to say, well, time isn't a factor when it comes to spotting differences between the two groups. And also, if you apply procedural control as well, you can say, well, after such and such time, we notice there's differences between these two distributions, and we can remove the baseline from the negative control group from the experimental group, and make sure we isolate the effect of the independent variable on the dependent variable. Okay, so let's start with hypothesis testing. We first want to introduce what the null hypothesis is. So when we're talking about a hypothesis and hypothesis testing, it's about us trying to test an assumption regarding a population's parameter. So we're going to start off by formulating a hypothesis called H1. So that's like our original hypothesis. Each main hypothesis, H1, will have a contradictory hypothesis, H0, and we call that the null hypothesis. So that's going to be what happens if your hypothesis is not true. It's going to be the null hypothesis, the exact opposite of what you're looking for. So if we can reject or accept the null hypothesis because it's easier to do so, then it's a lot easier to make predictions about our real hypothesis. So the first question is, why is it easier to analyze the null hypothesis? The main thing is, with the null hypothesis, we're testing a statement with a mean value, mu equals to something. So maybe our hypothesis is to say that, our value is not this, or our value can be greater or less than this value. In that case, your null hypothesis would assign a value that you want to disprove. So mu is equal to this, as a value that isn't suitable. So that means it's easier to disprove that mu is not one value than to disprove that mu is many values. So rejecting the null hypothesis usually concludes that our hypothesis is likely true. And the stronger you can reject the null hypothesis, the stronger you're confident, or the more confident you are in accepting the real hypothesis that you set out at the beginning. So I first want to go through what a one or two-tailed test of hypothesis is. So it's important to determine what kind of test you want to have when it comes to your hypothesis. If you have a one-tailed test, it means that you will only test to see if the parameter is significantly greater than or less than x, but not both. So in this case, our hypothesis can only be mu is less than x. So that means over here, maybe mu is less than a specific x, or mu is greater than x. So that means that our null hypothesis is simply going to be mu equals x. What are the chances of getting mu equals x? So if our test statistic falls within what we call a critical region, then we can reject the null hypothesis and accept the original hypothesis. So this is called the rejection region, or the critical region, with this being the critical value for the level of confidence you're looking at. So if I have a 95% confidence interval, then I'm looking at a 1.6 something standard deviation away from the mean, or the center of the distribution. So in that case, that means anything outside of this standard deviation is going to be called our rejection region. So if I have a confidence interval of 95% and I'm trying to test whether mu is equal to x, then that means with 95% confidence, I want to make sure that my value falls within this region. If my value falls outside of this region, then that's the remaining 5%. So if I have a one-tailed test of hypothesis, if I can prove that my value falls within the 5% either at the beginning or at the end of this distribution, then I can show that my null hypothesis is rejected, and and the true hypothesis is accepted with a 95% confidence, level of confidence. So what happens if you have a two-tailed test? If I want a 95% confidence interval, then keep in mind that you have to split the remaining 5% between the lower and the upper regions. So now my standard deviation is slightly different. It's going to be 1.96. So that's typical because most of these experiments that you do, they're going to have two-tailed tests of hypothesis. So in this case, you would make sure your 5% is split into your 2.5% at the beginning and at the end of your confidence interval. And so you have your lower and upper tails, and you're going to test to see if the parameter is significantly greater or less than x in either direction. So our hypothesis here is going to be mu is not equal to x. So then your null hypothesis is going to be mu equals to x. So therefore, determining whether you have a one or two-tailed hypothesis is extremely important because your analysis is going to change and your rejection region will change as well. So just keep that in mind as we go through the lecture because they'll come in quite handy as we work through how to calculate things through hypothesis testing. So now we want to see how we can approach hypothesis testing. The first thing is create a null hypothesis H0 and assign it a value. Then create a hypothesis H1, which is your alternative hypothesis, and determine whether it requires a one or two-tailed test of hypothesis. Then you're going to determine a test statistic and its p-value. So you're going to get a measurement, and then you're going to test the p-value or the probability of that value taking place. And if that value is very, very, very low, then that's good because it's very unlikely that the value will take place in the null hypothesis. So then you're going to determine the rejection region and test your p-value. And make conclusions from your results on your significance and confidence of your conclusion. So let's first go through what a test statistic is. A test statistic is a single number that's calculated from your sample data that we can use for a hypothesis test. So we basically assign the null hypothesis the value of our test statistic x. So then our goal is to test if this value x is similar to the population mean mu, which we're going to get from our null hypothesis. And then we're going to get a z-score through this equation where you have the mean minus the population mean divided by your standard deviation. From that z-score, you can then calculate a p-value. So that's something we'll go through in a bit. But from your z-score, you can construct a rejection region that's based on a chosen alpha level of significance, which correlates to what we discussed before for confidence intervals, 1 minus alpha level of confidence. So if I want a 95% level of confidence, then my level of significance would be 0.05. So usually we're going to use a confidence level of 95%, and then you're going to find the z-score of alpha over 2 for a two-tailed test for critical values. So let's go through what that means. This is a little bit blurry, but if I have a confidence level of 95%, this means that the majority of my values are going to fall between here and here. And I'm fairly confident that they will. So that leaves the two remaining tails to be our 5%. So then we use z of alpha divided by 2 to get our desired standard deviation a certain distance away from our origin. So that's minus 1.96 standard deviations away and plus 1.96 standard deviations away. So for this, it means that if we have any values that fall within these particular red regions called the rejection regions, we can immediately reject the null hypothesis with a certain level of confidence and say that the hypothesis we had from before is accepted. So let's now go through p-values and what they mean. So a p-value is basically the probability of seeing a select set of data if the null hypothesis is true. So with your z-score that we have from before of the test statistics and our desired confidence interval, we can easily find the probability of obtaining certain z-scores in our distribution. So if we have a probability density function for a measured value of x, like this, if we obtain an unexpectedly large value of x, we can test the p-value using the probability function. And here it's going to test for the null hypothesis. Basically, what are the chances that p is much larger than x? So if the p-value is 0.05 or lower for a confidence level of 95%, it means that we can reject the null hypothesis and say with the same 95% level of confidence that the hypothesis is true. So in this case, what I'm testing is, if I go back to this diagram, just go back. What are the chances that my value is greater than this right here? Then if I have a very low chance of being in this region, it means that I'm fairly confident my chances of being in this green region are much higher. So if I'm in this rejection region and I find a value within this rejection region and I prove that there's a very low chance of getting a value in this region, then I can reject the null hypothesis and show that I'm confident my value comes from this area. So just remember, rejecting the null hypothesis doesn't prove that the hypothesis is true. It just gives us a high likelihood that it is so. So as an example, for physics, in 2012, the Higgs boson was discovered. And that's basically a tiny fundamental physics particle, and it garnered widespread attention. Primarily during that time, after reading a bunch of articles, you'll notice that the term 5 sigma was thrown out quite a bit. So now you can fully understand and appreciate why that discovery was presented that way. When the scientists discovered discovered Higgs boson, they didn't present the probability that Higgs boson exists or not. They presented the probability that if the Higgs boson did not exist, what would be the likelihood of getting this data? So if the likelihood of getting that data is very, very little without the existence of Higgs boson, then that means that you've disproved or rejected that null hypothesis and therefore have accepted the reality that the Higgs boson does exist. It's a little counterintuitive, but basically the likelihood of getting the data without Higgs boson was given a p-value of 3 times 10 to the negative 7, which meant that there was a 1 in, I think, 3 million chance that the data would have been like that if the particle didn't exist. So therefore, they effectively rejected the null hypothesis, and that meant that the data could only be that extreme if the Higgs boson did exist. So acceptable errors, something else we have to take a look at when we're doing hypothesis testing. We know that in reality, our hypothesis can either be true or false. So that means with our hypothesis testing and strategy of rejection, our statements can only go so far. Sometimes we do make mistakes. So the worst thing that can happen if you accidentally say something is true when it's actually not, and vice versa. So we're going to outline 2 different types of error. Type 1 error is when the hypothesis is really true, or is when the null hypothesis is really true, but the statistical tests have led you to believe that it's false. So in that case, this is quite a damaging conclusion because you've basically created a false positive. And so when you're presenting your conclusion, it means that you've presented the opposite of what was actually taking place. And that's very hard to come back from. With a type 2 error, when your null hypothesis is really false, but the statistical tests show that it's true, that means you've indicated your hypothesis is incorrect and further experimentations have to be done. So this technically is less damaging because you haven't proved your hypothesis. Your hypothesis is going to live to see another day when further experiments are done. So in terms of the approach to hypothesis testing, let's try and use Python for this. The first thing is to create a null hypothesis and assign it a value. So we can easily set a value for the null hypothesis called mu equals to 10. So that's kind of acting as our expected value. We then create a hypothesis H1, which is our alternative hypothesis, and determine whether it requires one or two-tailed hypothesis testing. So we don't need code for this. We simply know that whatever our hypothesis is, it's such that mu is not equal to 10. And that means it's going to be a two-tailed hypothesis test because it can be above or below. So number 3, determine a test statistic and its p-value. So just keep in mind, p-values are usually represented as capital P, little p, italics p. As long as it's p-value, you know it's the chances of getting that value given the null hypothesis. So in this case, we have to set the test statistic, the standard deviation, the sample size, and find the z-score. So it says over here, these values would be given to you, and that's correct. For our hypothesis, these are values that we choose ourselves to prove or disprove. Then from your test, you'll be able to get a mean value from your experiments. Let's say you get 10.5. You get a standard deviation from your measurements, let's say 0.03. And then you have the number of measurements you take, which is 100. So you have these 3 values that are added into to your code. Then you're going to calculate the z-score based on the equation we presented before. It's going to be the difference between your measurement and the expected null hypothesis value divided by your standard or your variance. So it would be your standard deviation divided by the square root of n. So that gives you your z-score. Now, in Python, you're able to find the corresponding p-value for your z-score by using SF. So for a normal distribution, we're going to say the p-value is equal to scipy.stats.norm.sf of the z-score. Now keep in mind, this particular function is called the survival function, so it's what remains. So if I'm trying to figure out the p-value of the survival function, I then implement the z-score, but keep in mind, if I have a z-score and it's a two-tailed test, I have to multiply this by 2 to make sure that there's 2 tails known for this. So that is then going to give me the proper p-value for the proper hypothesis test that I'm using. If I simply have a one-tailed situation going on, then I just remove the multiply by 2. So after that, I should be able to get a p-value. And so if I have a p-value that's less than 0.05, then that means I've already satisfied with 95% confidence that it's very rare to get this null hypothesis value. In that case, I can determine the rejection region. I can test to make sure my p-value is less than 0.05 or even smaller. And then I can make conclusions from the results on significance, which is usually 0.05, and a confidence level of 0.95. So all the code you would need would just be for step 1, defining the null hypothesis, and step 3, which is trying to create the test statistic, the z-score, and then getting the p-value from that z-score. So after you're all done, you can go and make a conclusion and make inferences about the population. So as a summary, make sure you understand the idea of statistical inference through hypothesis testing and parameter estimation. Then you want to know the proper steps to experimental design, figure out what kinds of controls are possible and what are the pros and cons of each, know the steps to hypothesis testing and how to perform it using Python, and of course, understand all aspects of hypothesis testing, from the null hypothesis to a test statistic to acceptable errors, as well as whether you want to apply a one or a two-tailed hypothesis test to figure out your p-values. And that's about it. The next few chapters are going to be about how we can apply certain statistical tests to find our p-values in a much more automated way.